Dr. Stephen M. Barr is Professor Emeritus in the Department of Physics and Astronomy at the University of Delaware and Director of its Barr Research Institute. He received his PhD from Princeton and has held research positions at the University of Pennsylvania, University of Washington, and Brookhaven National Labs. Dr. Barr is a theoretical particle physicist whose research centers on grand unified theories and the cosmology of the early universe. He's authored over 150 papers and lectures widely also on the relation of science and religion. He is the founding and current president of the Society of Catholic Scientists. And we're glad to have him today for his talk, Is the Universe Made for Life? Anthropic Coincidences and Multiverse Ideas.
I thank the Lumen Christi Institute for inviting me to give this talk. And as you see, the title of the talk is the Universe Made for Life? Anthropic Coincidences and the Multiverse. Is the human race meant to be here? Or are we just a fluke in a meaningless universe? There are two very widespread and diametrically opposed views on this question. One is held by most theists, including Christians, Jews, Muslims, and the other is held by most non-religious people, including atheists. What is the Christian view? According to Scripture and Christian tradition, we definitely are meant to be here, and the human race has an important place in the divine plan. The letter to Diognetus, for example, a Christian work of the early 2nd century, said, God loved the race of men. It was for their sakes that he made the world. The first creation account in the book of Genesis reaches its climax with the creation of mankind. And the Apostle Paul told the Ephesians that they were chosen by God and destined to be his sons and daughters before the foundation of the world. On the other hand, many atheists tell us that science has shown that the human race to be just an accidental byproduct of blind material forces in a universe that has no point or purpose. Bertrand Russell wrote that man is a, quote, curious accident in a backwater of the universe. A classic statement of the atheist position was given by the physics Nobel laureate Steven Weinberg, who died just a few months ago. In his 1977 bestseller, The First 3 Minutes, A Modern View of the Origin of the Universe, he famously wrote, "It is almost irresistible for humans to believe that we have some special relation to the universe, that human life is not just a farcical outcome of a chain of accidents, but that we were somehow built in from the beginning. It is very hard for us to realize that the entire Earth is just a tiny part of an overwhelmingly hostile universe. The more the universe seems comprehensible, the more it also seems pointless." Weinberg's view is understandable. The universe is indeed inconceivably vast compared to the Earth and its inhabitants. The human race is indeed the outcome of a long chain of events that could have gone otherwise. The forces of nature, while not literally hostile to us, are certainly blind, unfeeling, and harsh. The universe goes about its business without any concern for us. Tsunamis are unaware of the villages they drown, or tornadoes of the devastation they wreak. As the atheist biologist Richard Dawkins is wont to remind his readers with evident and perverse relish, nature's relation to us is one of pitiless indifference. Isn't it foolish then, as Weinberg suggested, to imagine that we were somehow built in from the beginning, in his phrase, and meant to be here? Hasn't the whole thrust of modern science, from Copernicus and Darwin down to the discoveries of the last century, been away from such naive anthropocentrism? Hasn't the story of science been about the successive dethronement of man as the Harvard biologist and popular science writer Stephen Jay Gould used to say. Well, maybe not. It's beginning to look very much like we may have been built in from the beginning, at least in some sense, after all. In the last 50 years or so, particle physicists and others have begun to notice that many features of the fundamental laws of physics and the structure of the universe appear to be just what is needed for the existence of living things such as ourselves to be possible. These features are often called anthropic coincidences. Why are they called that? Well, anthropic, the word coincidence points to the fact or claimed fact that some features of the laws or structure of the universe happen to coincide with what is needed for life. The word anthropic comes from the Greek for human being. It's not the best adjective to use because what's at issue in most cases is the possibility of living things of any kind, not just of human beings. Now here I must digress to say that I am not using the term anthropic principle, which probably most of you have heard of. Anthropic principle is really a very bad term for many reasons. For one thing, different people mean very different things by it. And all of those different meanings refer to ideas that are proposed as explanations of the coincidences. Some of those proposed explanations are flaky or tautological, and none of them deserves to be called a principle. So it would be best if the term anthropic principle were never used. Unfortunately, it has caught on and is here to stay. But I must repeat that I am not talking about any such so-called principle. I'm talking about anthropic coincidences, a very clear term with a single agreed-upon meaning, which refers to something that is increasingly accepted as having a firm factual basis. Now, to return to my talk. Until about 30 years ago, it was almost taboo to mention, let alone discuss, anthropic coincidences in the physics research literature. The idea that there might really be such coincidences, or if there were, that they had any significance, was generally dismissed out of hand as unscientific. There are a number of reasons for this, which we could talk about later in the Q&A if you like. One reason was expressed rather concisely by a Nobel laureate in my field, in particle physics, who declared that he hated the subject because, quote, it smells like religion, unquote. Gradually, however, attitudes have changed, in part because a number of leading physicists, many of them avowed atheists, including Steven Weinberg himself, began to take anthropic coincidences seriously as calling for explanation. It's now fairly widely admitted, I'm not saying by a majority of people in my field, but it's fairly widely admitted among particle physicists that some of these coincidences are real and may be telling us something important about the world. For example, the late Stephen Hawking and Leonard Mlodinow, in their 2010 popular book, The Grand Design, wrote, quote, "What can we make of these coincidences? Our universe and its laws appear to have a design that is tailor-made to support us, and if we are to exist, it leaves little room for alteration. That is not easily explained and raises the natural question of why it is that way." Ed Witten, widely regarded as the most brilliant theoretical physicist in the world, who has called himself a skeptical agnostic on religious questions, said in an interview, quote, "The laws of nature are very delicate. The fact that galaxies, stars, and planets, roughly like ours, could have formed, and that living things, roughly like us, could have formed, depends on many details of the laws of physics as we currently know them, being just the way they are and not being slightly different." I think we'll never resolve the sense of wonder about that. Before going into the question of the possible significance of anthropic coincidences, it may be helpful to give some examples of them. Those who want to see more in-depth discussions can refer to a number of technical articles as well as several popular books written by physicists. There's not a lot of space to write many technical articles. There's papers. There's one, a very important one by Carr and Rees, Sir Martin Rees, it published in Nature a long time ago, called The Anthropic Principle and the Structure of the Physical World. And there's a few others, and I list on this slide, I think, it was 5 books, popular books, by physicists discussing them in some detail. Now, a famous anthropic coincidence has to do with the so-called strong force, one of the 4 known forces of nature. There's electromagnetism, gravity, the strong force, the weak force. Really, one should also add the Higgs force. Really 5 forces of nature that we know about. The strong force is the one that binds neutrons and protons together to make atomic nuclei. Now, if this force had been weaker by even about 25% than it is in our part, at least in our part of the universe, then we wouldn't be here. Why is that? Because it takes atoms of many types to build a living thing. For example, a human body contains 25 different chemical elements, at least the last time I asked a biologist. He told me it was 25 elements, including hydrogen, carbon, nitrogen, oxygen, sodium, phosphorus, iron, and 18 others. Where did all these elements come from? Very early in the history of the universe, ordinary matter consisted of just isolated protons, isolated neutrons, isolated electrons. A proton is the nucleus of a hydrogen atom. Don't take this picture too seriously. It's kind of appears in elementary books. It's very schematic and simplistic, but it gets the point across that I want to make, which is the hydrogen atom has a single proton in its nucleus. Now, if you remained with just isolated protons, neutrons, and electrons, the only element that you would have would be hydrogen. To make all the other elements of the periodic table, you have to start putting protons together with neutrons, because all the other elements in the periodic table have nuclei that consist of a collection of protons and neutrons. Now, to make all of those roughly 100 or so elements, you start what happened historically, in the history of the universe, is first, and look at the top part of the picture where the protons are drawn in blue and the neutrons in yellow, is you have one proton and one neutron stick together to form something called a deuteron. Then another particle comes along, say another neutron, and sticks to that to make something with 3 particles in it called a triton. Then comes along another proton and sticks and forms something that's called an alpha particle, or equivalently, it's also the nucleus of ordinary helium, helium-4 nucleus. And so it goes. You keep adding more, sticking more, the smaller nuclei together to form bigger nuclei and bigger nuclei until you build all the way up to uranium, which has 92 protons and 143 neutrons in the case of U-235. So that's the process. Now, all of that happened, the sticking together of smaller nuclei to make larger ones is called nuclear fusion. And it happens primarily inside stars. Most of the elements in our body, except for hydrogen, which has been around since the Big Bang, most of the elements in our body were made in these fusion reactions taking place inside stars. And those fusion reactions release energy, and that's where the energy of the sun comes from, those fusion reactions. Now, if the strong force had been about 25% weaker than it is, then it would not have been able to stick together a proton and a neutron to make a deuteron, which is the first step in the process by which all the elements are made. And so the universe, what's called nucleosynthesis, the making of the different elements, of the nuclei of the different elements, couldn't have gotten off the ground. You would have been left with the universe with just hydrogen. And I don't think anyone believes you can make life, at least life based on chemistry, with just hydrogen to play with. Now you might ask, what if the strong force had been, so we wouldn't be here. What if the strong force had been a bit stronger than it is? Well, that's actually much more complicated to analyze. In that case, one thing we know is if it was just a few percent stronger, then it would have been able to bind together two protons, which does not happen in the universe that we live in. And it would be able to directly bind two protons together, and that would have radically changed the way stars burn their nuclear fuel. It has been argued by some that it would make, you would not have stars that were just like the sun. Stars would have been, hydrogen-burning stars would have been quite different, and whether they would have had the properties you need to be able to have sustained life on their planets is unclear. But it's quite possible that you would not have gotten the right kinds of stars to support life. So the strong force seems to be in a sweet spot. Not too strong, not too weak. Another famous anthropic coincidence was noticed in the 1950s by the astrophysicist Fred Hoyle. And it has to do with the so-called 3-alpha process, or triple alpha process, which is the process that has produced essentially all of the carbon in the universe. This process takes place inside stars, and it involves 3 helium nuclei, also called, as I said, alpha particles for historical reasons, happening to collide, 3 alpha particles happen to collide almost at exactly the same instant. And they fuse to form carbon-12. Why do 3 have to collide at the same instant? Why couldn't you have 2 alpha particles, or helium-4 nuclei collide, stick, in which case they would form something called beryllium-8, and then, at some later time, a third one comes along and sticks to that? Well, this somewhat busy picture explains what happens. You read from the top down. So it shows 2 nuclei coming together into a blob, which is labeled Be, beryllium-8. And as the purple letters say under that blob, highly unstable. They don't remain stuck together. They only remain stuck together for about 10 to the minus 16 seconds, or a tenth of a millionth of a billionth of a second. Actually, in nuclear physics terms, that's a very long time, but it's very, from others' points of view, it's very short. And then they, as it says, almost always just fly apart again. So the third helium-4 nucleus, or alpha particle, has to come along in that little sliver of time while they're still together to stick to them to form carbon. Now, as you might imagine, that's a very unlikely thing to happen. And you might not get very much carbon out of that. And in fact, Fred Hoyle calculated how much carbon you would get, and you get very little. So that puzzled him, because there's a lot of carbon in the universe, fortunately, because you need it to make living things, all the kinds of living things we know about. So he realized something must enhance that 3-alpha process. Something must give it a little extra juice so that it happens more often. And it turns out it is enhanced. And the reason it's enhanced is that the carbon-12 nucleus that you form has what's called an excited state. It's basically a mode of vibration. It has just the right energy to what's called resonantly enhance the process by orders of magnitude. If the energy of that excited state were a percent or so higher or lower in energy, the process wouldn't be resonantly enhanced. You get very little carbon and probably no life. A more dramatic example of what's called anthropic fine-tuning was pointed out by me and 3 collaborators in a paper we wrote in 1998. And there's actually an interesting story about that, which I could tell you in the Q&A. There's a parameter in our present fundamental theory of physics called the Standard Model of Particle Physics. Our present theory of physics, of all of physics, has two parts. There's Einstein's theory of gravity, or general relativity, which describes gravity. And then there's the Standard Model of Particle Physics, which explains everything else. Now, the Standard Model of Particle Physics has in its equations a parameter which is called little v, which is short for the rather forbidding technical term vacuum expectation value of the Higgs field. This parameter v is very important. It's like a knob that controls the many basic things in the world. It controls, for example, the masses of many basic subatomic particles, such as electrons and quarks. It controls the strength of the weak force, which is one of the four fundamental forces that we know of. And indirectly, it affects many other features of the physical world. It turns out that the numerical value of v has to lie within an extremely narrow range of hypothetically possible values if life is to be possible. If the value of v were significantly larger than it is, it turns out all neutrons would have decayed into protons, making hydrogen the only element, because all the other elements of the periodic table have nuclei that contain both neutrons and protons. If all the neutrons decay into protons, even in nuclei, it turns out you really won't have any stable nuclei except hydrogen. Now, if v had been even larger, in fact, if v had made v even larger than that, not only would neutrons have all decayed away into protons, but neutrons and protons would all have decayed into an exotic particle called the delta plus plus. And those would have formed atoms, indeed, but the atoms would have chemically acted like helium, which is an inert element. And so you would not have had interesting chemistry, and you would not have had life. Now, you might say, what if v had been smaller than we see it to be? What if it had been on the low side? Well, then, certain quantum processes that are exceedingly rare in our universe, called Sphaleron processes, would have happened very easily and erased all the ordinary matter in the universe, meaning that there would be no atoms at all. So v is in a very sweet spot for life. Not all anthropic coincidences have to do with certain quantities being fine-tuned to have just the right values, like v and the strength of the strong force. Certain gross qualitative features of the universe and its laws are also important for making life possible. So I'll give a couple of examples of that. An especially important example is that the universe is governed by the principles of quantum mechanics. Quantum mechanics tells us that at very small distances, the physical world is grainy rather than smooth. The very fact that matter is made up of particles, such as protons and electrons and so forth, out of which complex structures can be built, including living things, is a consequence of this quantum graininess. Moreover, the structures built out of those particles are only stable because of quantum mechanics. It is the fact that electrons act in a quantum mechanical way that prevents electrons from getting pulled inside atomic nuclei by their electrical attraction, causing all matter to collapse catastrophically. As you know, an atom consists of a positively charged nucleus and negatively charged electrons. If we lived in a classical, that is a non-quantum mechanical universe, the electrons would simply get sucked into the nucleus by the electrical attraction and remain there. Atoms would collapse, matter would collapse. Moreover, even if somehow you could make atoms in a non-quantum mechanical universe, keep that disaster from happening, and you can keep the electrons orbiting the nuclei in a stable way, They would have an infinite number of ways of doing that, meaning that no two atoms would be alike, and no atom would behave consistently over time. Matter would be constantly and very rapidly morphing in unpredictable ways without stable properties. There's other things that quantum mechanics does that are nice that I won't go into. Quantum mechanics is very strange, but many of its strange features are very good. That is are very fortunate for us. The ability of the universe to have life also depends greatly on the kinds of particles that exist and their properties. It's especially important that there are particles with the properties of electrons, neutrons, protons, photons, pions. Each plays crucial roles. There are many particles that seem not to play any practically useful roles, but some of them do. It's very fortunate that some particles of these types exist. The same is true of each of the known fundamental forces, which I listed before. For example, electromagnetism holds atoms, molecules, and all ordinary matter together. It also gives rise to the existence of light. The strong force, as already mentioned, binds atomic nuclei together. Without it, nuclei would fly apart due to the electrical repulsion of the protons in them. The strong force also provides the nuclear fusion energy that powers stars, which in turn is needed to warm planets and generate the energy needed to sustain life and to evolve life in the first place. Without gravity, matter would not be condensed into stars or planets, nor planets retain their atmospheres. Moreover, the gravitational expansion of space and at the time of the Big Bang, and the gravitational clumping of matter in the early universe was key to generating the reserves of all of the usable energy in the universe, which all life in the universe depends on. The weak force makes possible certain nuclear reactions that generate the energy of stars like the sun. The Higgs force is needed to give mass to particles such as electrons and quarks. I'm just giving some examples. It's very important. The richness of our universe depends on there being a whole set of actors who have certain characteristics. It's not only the existence of these forces, but their specific characteristics, their delicate and complex interplay, and the fact that their strengths are in just the right relation to each other that makes life possible. To take one of many examples, so it is important for the existence of a rich variety of stable elements that the mass of the proton and neutron be almost equal to each other, but also that the mass of the neutron be slightly larger than that of the proton. It turns out otherwise, if they were very disparate in their mass, or even if they were similar, if the proton were slightly heavier, then either all protons would decay into neutrons or vice versa, which would have made almost all the elements of the periodic table unstable. And in fact, neutrons weigh 939.6 million electron volts, whereas protons weigh 938.3, 939.6, 938.3. They're within about 1 part in 1,000. They're almost exactly the same mass. And, as it happens, fortunately, it is the neutron that is slightly heavier. This is a case where the buttered bread fell, where Murphy's law did not operate, and the right particle had the larger mass. Now, this near equality of their masses is due to certain properties of the strong force, while the fact that the neutron is slightly heavier is due to the way that the Higgs force affects quarks. So this is an example of how the different interplay of different forces makes life possible. The characteristics of space and time are also critical. We take for granted that there are 3 space dimensions and 1 time dimension. There's no law of logic that says the world had to be made that way. Particle physicists study hypothetical universes whose spaces have different numbers of dimensions. Indeed, in superstring theory, which many experts think may be the correct unified theory of all the forces of nature, there are 9 space dimensions, 6 of which are crumpled up into little surfaces of subatomic size, and 3 of which are large. It seems to be crucial for life that there are exactly 3 large dimensions of space, as in our universe. If there were more than 3, the force of gravity between 2 objects would depend on their distance from each other in a different way than in Newton's law, than Newton's famous inverse square law. Gravity in such a universe with more than 3 space dimensions would be comparatively stronger at short distances and weaker at large distances, which means planets would either be sucked into the stars, or they would fly off into space. There would be no possibility of them stably orbiting stars. And that's actually an easy homework problem, which I would do for you on the blackboard if I had the time. So it's very important. And not only that, if there were more than 3 space dimensions, atoms would be unstable for a similar reason. Electrons would either be pulled into the nucleus by the electrostatic attraction or fly off. Now, so I think I've given, what if there were fewer than 3 dimensions? Well, then other things go wrong, but I'm going to skip that for reasons of time. So turns out 3 dimensions is very special. So this is a small sampling of the many anthropic coincidences that physicists have discussed. By the way, remember Hawking said there are many features of the laws of physics that seem to be tailor-made for life. What is one to make of them? One rather obvious possibility is that a mind framed the laws of physics of this universe and did so with the intention that it should bring forth living things, including beings such as ourselves. That certainly accords well with the Christian view, or generally the theistic religious view. There is, however, another way to explain at least some of these anthropic coincidences, which does not invoke God, and it's called the Multiverse Hypothesis. Now, the multiverse idea is a very speculative idea and comes in a variety of versions. There are many misconceptions about the idea floating around in the public. First of all, it's not the same thing as the many worlds interpretation of quantum mechanics, and has no necessary connection to that idea. Second, the multiverse idea does not necessarily posit the existence of many universes. The versions of the multiverse idea thought about by most physicists all assume that the multiverse is a single universe governed by a single set of fundamental laws that apply throughout. Now, it's true that in some versions, I say there are many versions of the multiverse idea. In some versions, one has the universes splitting and recombining. But nevertheless, all of those recombining and splitting universes form a single interacting system, all governed, that whole system is governed by some set of fundamental laws. What makes a universe a multiverse is that the fundamental laws of physics have a flexibility that allows certain physical quantities and features that were traditionally thought to be the same everywhere throughout the universe to vary from place to place. For example, the strength of the strong force might be one thing in our part of the universe and different in other parts of the universe beyond our horizon, or the types of particles that exist, their properties, the value of V that I talked about, and so on. They could be different in different regions or domains of the universe. Now, if that were so, it could be that if there were a sufficiently large number of such domains, there could be a high probability that in at least some of them, all of the physical quantities and qualitative features would be just right to make life possible. That's the idea. Of course, to account for all the anthropic coincidences, the multiverse would have to be such that all the quantities and features that have to be just right for life all those quantities would vary from place to place, and not only that, they would have to vary over a sufficiently wide range of possibilities to include the just right ones. Now, in other words, the multiverse would have to be extremely rich in the possibilities that were realized in its various domains. Now, to many people, including many physicists, the multiverse idea sounds far-fetched and even kooky. Some religious people therefore imagine that it is just a desperate idea cooked up by atheists to avoid the obvious conclusion that the universe was designed with us in mind. But these dismissive judgments are not really fair. In the first place, many, and probably most atheist scientists, dislike the multiverse idea. Many of them intensely dislike it. The main reason is that it seems impossible to, the multiverse idea seems to be impossible to test by any observation or experiment. You see, the quantities and features that are postulated to be different in other parts of the universe are known not to be different in the whole part of the universe that we can see, that we can observe. The masses of the particles, the strengths of the forces, the value of V, all these things are known to be the same with great accuracy, to be the same throughout the entire what's called observable universe. There are parts of the universe we can't observe because they're too far away, and light from those parts of the universe would not have had time to reach us since the Big Bang. So those lie outside what's called our horizon, which is tens of billions of light years away. Within that vast observable universe, these quantities do not vary, which means what the multiverse idea is postulating is something happening, these quantities varying outside our horizon, which it can't test by definition. They're outside our horizon. So most people think, has good reason to say, that the multiverse idea is intrinsically untestable by us. And many people would therefore say it's not science. It doesn't belong to empirical science. It's simply philosophical speculation. And many atheists in particular are atheists because they say the existence of God is untestable. Scientific atheists, that's one of their main objections to religion, is God's existence is scientifically untestable. And so they hate the multiverse idea for the same reason. It's scientifically untestable. So that's one thing. And the other thing is that it's not a kooky idea from the point of view of particle physicists. Maybe because we're all kooks. But the fact is, from the viewpoint of our current understanding of how the physical world works, the multiverse idea does not look far-fetched. Okay. Now, for that reason, even though many atheists reject the idea as untestable, and therefore they would even say meaningless, certainly not science, it is true that there's some atheist scientists, for example, the late Stephen Weinberg and the late Stephen Hawking, who have realized that the multiverse is actually the only hope of explaining the anthropic coincidences in a naturalistic way without invoking God. And they have therefore been willing to swallow whatever epistemological scruples they might have had and embrace the idea. Okay. So I'm not going to say any more about the multiverse idea, except that it is not an unreasonable speculation, and it could explain many of the anthropic coincidences. Now, but I would say this. There is, in order for the multiverse idea to be correct, well, I think this is the takeaway lesson from anthropic coincidences. If you want to have living things in your universe, and you're designing a universe, you must give the fundamental laws of your universe must be very special in one way or another. They could be very special in having many quantities have just the right values. Or the fundamental laws could be very special in that they have a remarkable flexibility that allows many quantities to vary widely in different parts of the universe. That also requires the fundamental laws to be very special. And so the point is, one should not take for granted that the universe has these laws that are just right for life. That's not something that you would a priori expect. It is rather something that we should provoke in us wonder, as Ed Witten said in the passage I quoted before. He said, I think we'll never resolve the sense of wonder about that. And remember, he's a skeptical agnostic. He's not saying that for religious reasons. So that's the bottom line. The laws, you need to have special laws if you're going to have a universe with life in it. Okay, so having said all that, we remain with a question that's very troubling to many people, at least many religious people. Why is the universe so large? It's something that Weinberg referred to in the passage I quoted. We're just a tiny part of an overwhelmingly hostile universe. This is something that people have wondered about, religious people, for millennia. The psalmist asked, he said, when I consider the moon and the stars, what is man that you care about, that God cares about? Pascal, in his Pensées, says, the eternal silence of the infinite spaces frightens me, he said. So if we claim to be important in the universe in some way, why is it that the universe is so vast compared to us? Why would God have chosen to create a universe with such a vast amount of empty space, useless, wasted space? Well, actually, it turns out that there are a couple of good answers to that. One answer is very traditional, and there's a religious answer. The universe was not made only for our benefit. As Psalm 19 declares, the heavens proclaim the glory of God. Actually, Catholic doctrine says that the primary reason for God creating the world is to manifest his glory. Now, if it is the glory of God that they proclaim, then there's no particular reason why they should have to be made to human scale. In fact, an important thinker of the 15th century, Cardinal Nicholas of Cusa, argued that a universe of infinite extent would more aptly reflect the infinite splendor of God. Now, that's a good answer, but there's another. It turns out that the very age and vastness of the universe themselves have anthropic significance. Life emerged in our universe in a way that required great stretches of time. Most of the elements needed for life were made, as I told you, deep inside stars through fusion processes. And those processes, that whole process of synthesizing the elements and then through supernova explosions distributed them in space where they could be used, that required billions of years. And then once you have the elements you need for life, it takes further billions of years to go to first of all have life begin, and then have it evolve from single cells all the way up to creatures like us. So you need a universe that lasts billions of years. At least if the laws of physics are anything like the laws of our universe, you need billions of years. Moreover, there's a connection in Einstein's theory of gravity between the longevity of a universe and how large it is. So that, for example, suppose you said, I don't think God should have made the universe more than a few thousand miles across. That's all you need for living beings. Maybe he shouldn't have made, why did he have to make the universe any bigger than, say, the Earth? Well, a universe that was only thousands of miles across would last for only about of order 100th of a second, not billions of years. Even if you allowed God to make a universe the size of our solar system, which is still vast compared to human scales, it would only last it for a matter of hours. If you want the universe to last for billions of years, as needed to produce creatures such as ourselves, and if the laws of physics are like the ones we know to exist, to be true, the universe has to be billions of light years across as we see it to be. So the point is that the vastness of the universe, both in time, scales of time and distance, rather than pointing to our insignificance, are preconditions for us to be here. So that the frightening expanses that are so often said to be a sign of our insignificance are not signs of our insignificance. They are signs, perhaps, of our importance. And so, like many other features of our strange universe, they point to man, as they also proclaim the glory of God. Thank you. I like the physics questions especially. I talk a lot of physics in it. Yeah, hi, Stephen.
So, if there's a multiverse, does that imply that we haven't figured out enough forces yet? Because what accounts for the variability of the forces in different parts of the universe?
Okay, yeah, that's a very good question. Why? So the question is, what accounts in a multiverse scenario? What would account for forces and other things such as the masses of particles and strengths of forces and so on? I mean, different in different places. Well, what happens in some theories, and not just multiverse theories, but actually certain rather garden variety theories. So I've spent a lot of my career working on what are called grand unified theories. They've been around since the early 1970s. And they are theories which give a unified mathematical description of the three non-gravitational forces, electromagnetism, the weak and the strong force. There's a lot of circumstantial evidence in favor of grand unified theories, though there's no smoking gun experimental test yet, sad to say. Now, if you take some actually fairly simple grand unified theories, in particular certain what I call supersymmetric grand unified theories, what happens is the equations have more than one solution. There are certain variables that, to be more technical, that want to sit at the minimum of some potential. And the potential has multiple minima. And so the variable can sit at any one of those minima. And depending on what minimum it sits at, you actually get a universe that looks very different. In these grand unified theories, for example, depending on which minimum the variable or the field sits in, you could have different forces altogether. Now, those are not rich enough in possibilities to give you the kind of multiverse you want. There's only a few possibilities. And what would think in that case is what you need, first of all, is the universe to be vastly bigger than the observable part. And actually, there are very strong reasons to believe that the universe is exponentially larger than the part we can observe. It has to do with something called cosmic inflation. Then there are parts of the universe that are so far apart from each other that they've never had time to talk to each other, to interact. And so what would happen in a situation such as I was describing is one part of the universe, the variable would fall into one minimum, but in a remote part that's causally not in contact with it, it has no reason to fall into the same minimum. It might fall into a different minimum. So very far apart places the laws of physics would find different solutions, would have different solutions realized. And that's basically, and it's analogous to phase transition. So we know that H2O, to take a sort of a mundane example analogy, H2O can exist in the form of ice or it can exist in the form of water at the same temperature, at the freezing point. And you can have in the same room that's at the same temperature, you could have the water in one part of the room be in the form of ice and another part be in the form of water. In your glass of ice water. In some points of space, it's ice, and in a nearby point of space, it's water. So H2O can exist in different phases. And so the idea is you have a very large universe, and different parts of the universe are in different phases. And those phases can look so different that they seem to have different particles, different forces, different strengths of forces, and so on. Although they all are governed deep down by the same set of fundamental laws, just like H2O, whether it's ice or water, is deep down governed by the same laws of chemistry and physics. So sorry for the long answer, but that's a really important question. And so that's why multiverse idea is not so nuts. It's actually, I'll give you a glimpse of what goes into them, and it's not at all from a physics point of view crazy.
Question online.
So I've got two brief kind of clarifying questions.
Yes.
One is, can you explain why a small universe cannot exist for a long time? And then the second one is, how divisive is the theory, the idea of anthropic coincidences in the scientific community? How would you be received by your...
Oh, okay. I'm glad you asked because let me tell you an anecdote. Well, first of all, the universe cannot just be static. It's either expanding or contracting, basically. Just like you can't have a ball just hover in midair. If you see a snapshot of a ball up in the air, you know it's either going up or coming down. It can't just stay there. So we know from Einstein's theory of gravity, the universe is dynamic. In fact, it's expanding. And it turns out that if you try to build a universe and say the universe never gets bigger than a certain size, say 1,000 miles across, it's going to eventually, well, one of two things will happen, either collapse or it'll expand. And the rate, space and time are related to each other in Einstein's theory. Let's take the collapsing option. If it's small, it collapses and takes very little time to collapse. If it's very big, it takes a long time to collapse. You can see there a very simple, obvious relation between size and time scales. But even if in an expanding universe, it turns out that there's a relation between. But let's get to the question of, but I don't want to write down all the equations because first of all, I'm tired and I'd probably write them down wrong. I'm not the person pushing this idea. This idea has been around for 40 years, and many big name scientists in my field, not only Weinberg and Hawking, but Andre Linde, Frank Wilczek, I could give you a long list, Sir Martin Rees. Many very big name people actually take this anthropic coincidences very seriously. However, as I said, it was at one point almost taboo to talk about them. And that was not just because, partly for philosophical reasons, it sounded like introducing teleology back into science. I explain such and such by referring to what you need for us to be here. It sounds like it's anthropocentric, or at least life-centric, and it's saying this is the way it is because that produces such and such an effect. It's explaining the thing not by what caused it, but by something that it causes. And that's going back 400 years before modern science to Aristotelian type of teleology. But there's a whole range, and some people, because it sounded like it's an argument for God, and so it smelled, as this famous physicist so it said, it smells like religion, and so on. Now, the first person to write a really major research paper on anthropic coincidences was Steven Weinberg. I think it was 1989. I might have the date wrong by a couple of years. He could get away with it because he was numero uno in the field. He's a Nobel Prize winner and generally regarded as the top guy in the field. And he was also known to be an atheist. So he could write a paper, and he did, explaining pointing out a certain anthropic coincidence, a very big one, having to do what we now call dark energy, and explaining it with the multiverse idea. But very few people had the courage to write papers on that because it could ruin your reputation, make people think that maybe you're religious or maybe you're a kook. Now, at a certain point, I started thinking just out of curiosity about a particular very important question in physics, one of the big unsolved problems, having to do with this value of V. The value of V is a big mystery in particle physics. Its natural value, in a certain sense, which I won't explain, is about 10 to the 19 GeV. That's what you expect it to be. But it's actually only about 100 GeV, actually 174. That's 17 orders of magnitude too small. Why? That's a gigantic problem. It's perhaps the central problem in particle physics. Well, it turns out you could explain it anthropically, so to speak, in a multiverse scenario. You could say, well, you could either say, anyway, it turns out that the small value is needed for life. It has to be about 100 GeV. So I actually worked out a number of arguments to that effect, but I didn't publish them because I had a good reputation in my field and I didn't want to ruin it. But one day I was talking to a very eminent scientist who had been the editor of a journal called Physical Review. This guy is a pillar of the community. And he asked me at lunch one day at a conference what I'd been thinking about lately, and I told him, and he listened, didn't say anything. But then about a year or two later, he emailed me and said, Steve, I've been thinking, that thing you were telling me back in a couple of years ago, I've been thinking along similar lines, and I have some ideas. Why don't we join forces and write a paper on it? Well, I figured, okay, that gave me cover, because this guy is a pillar of the community, and no one's going to think that he's off his rocker. And so he and I, and one of my colleagues, who's actually a very strongly atheistic, and a grad student wrote a 4-person paper, and we had a hard time getting it published. And here, it's a funny story about that. If I have a minute? A minute. We submitted a long version of the paper to something called Physical Review, which is actually not hard to get published in unless your paper is grossly wrong. But we wrote a condensed version and sent it to Nature. Nature immediately rejected it because it said it was not sufficiently fundamental, which is absurd because it was actually one of the most fundamental problems in the field. So then we said, to heck with them. We sent it to Physical Review Letters, which is the letters version of Physical Review, which is a very prestigious journal, like Nature, and very hard to get published in. Well, the 2 referees in Physical Review said the paper was okay, it could be published, but it got vetoed by the editor, who said, I'm taking the almost unprecedented step of vetoing the referees, overriding them, and he wrote a 10-page rant saying that this was not even science. Meanwhile, Physical Review Letters accepted it, and that's the much harder journal to get in, and both referees said it was a good paper, should be published, and one of those 2 referees we learned was Stephen Weinberg. So you had the top guy in the field saying it's good enough to be in Physical Review Letters. He said it's so embarrassed with Physical Review for rejecting it that they first. Now, since then, the climate of opinion has completely changed because a lot of people think that superstring theory may be the right theory of fundamental theory of physics, and it's beginning to look like if superstring theory is correct, we live in a multiverse whether we like it or not, and that many parameters actually vary from place to place. And so now it's no longer taboo to write about anthropic coincidences. There are tons of papers. And that paper we had a hard time getting published has now, I think, have ordered 250 citations, many of them being top people. So I just thought I'd tell that story. That's how people look at it. The climate of opinion has greatly changed.
Yeah, I have a question. So you said just to follow up on that, you said the climate of opinion is changing. Is it becoming more teleological, or is this getting lost over time?
No, not more teleological. See, in a way, it doesn't matter. The coincidence you establish. Are people getting more teleological in their thinking? Is the climate of opinion changing in physics in a more teleological direction? No. What's happening is, when you talk about anthropic coincidence, all you're really saying is this. Here's an aspect of the laws of physics. What would happen if that feature of the laws of physics or the structure of the universe were slightly different? And you look and you think about that, and you claim, or you argue, if this feature was slightly different, then there wouldn't be life. Then if you can succeed in arguing that convincingly, then you've established that this is an anthropic coincidence. You can take 2 or 3 attitudes, actually, towards that. Okay, interesting, but that's just a pure coincidence. B, well, God, that points to God. God set it up that way so there'd be life. C, it's a multiverse. But simply pointing out the coincidence has, in and of itself, is just pointing to a fact that you might be able to demonstrate by simple physical calculations. And so people are now more tolerant of the idea that there are anthropic coincidences. Most of them probably go for the multiverse idea, which is not teleological. It's no more teleological. It's really a generalization of the idea. Why are conditions on Earth favorable for life? If it were much hotter, all the water would boil away. If it were much colder, it would all freeze. If the gravity were stronger, we'd all be crushed by gravity. If the gravity were weaker on Earth, we'd lose our atmosphere. Lots and lots of things, the chemical composition of the crust of the Earth, lots of things are favorable for life. Well, in that case, why is that? Because there's a tremendous number of planets in the universe, and some are hotter, some are colder, some are larger gravity, some are smaller, different chemical composition. There are at least 10 of the 22 planets in our observable universe. It's not surprising that some of them are habitable. In fact, we now know that a very significant fraction of them are habitable. It's not teleological to say that, and so the multiverse idea is not teleological either. So it's just that people are less nervous about talking about it. That's all. And they're sort of forced to that because of superstring theory, as I said.
We have time for another question?
Just a last question about, you were talking about the 3 different views. Is there anything that would preclude, there being a God if you were to say that you look at it and you see that it is a multiverse? I mean, it seems to me that B and C are compatible.
Yes, that's a great question. Do you have to choose between the God explanation and the multiverse? Not at all. I tend to think we probably live or I think it's very possible that we live in a multiverse. It's not unlikely. Let's put that. I don't think it's not unlikely that we do, but I also happen to believe in God. And in fact, that was the point I made here in this slide. You need special laws. Even to have a multiverse, the laws have to be special. So if you're some deity or whatever, building universes and you're picking laws, and there's an infinite number of possible mathematical laws you could pick for your universe. I don't think one can quantify this and do a probabilistic calculation, but I would say that in some loose sense, you would not expect that if you took some random set of laws that they would lead you to a rich enough universe to have life in it. You need those laws to be special in one way or the other. And I think that's not a proof of anything. But it certainly gives the lie to what Weinberg said in his book in the 1970s, where he said the more we learn about the universe, the more it seems pointless. He didn't think you could prove it was pointless. He said, prima facie, it looks like the universe is pointless. Well, now, prima facie, it looks like it isn't pointless. That is, on the surface of things, the laws are actually just right for there to be life. That at least suggests that the universe is not pointless. Now, you could explain those appearances by a multiverse. That's actually the only way you could really explain it naturalistically. But it's certainly at first blush, the more we're learning about the universe, the more it seems to have a point.
Should you have time for one more question?
So conceptually, if you're talking about the multiverse, where there's potentially different regions where not just one thing is changing, but a whole slew of different things are all changing at the same time. We happen to be in one part of it where things appear to be sort of very special, as you put it, to have given rise to us. Does that imply that there are other regions, even hypothetically, where there could be another set of special sort of variables where other forms of life pop up?
Yes. In fact, one of the criticisms of so, for example, I said that if you change the value of the weak scale, V, sometimes called the weak scale, that would make life impossible. But if that's the only thing you changed in the standard model of particle physics, there's no question about it, that if you change it too much in one direction or the other, you won't have life. What if you change two things at the same time? Well, there are papers in the literature saying if I changed that, even if I made V very large, but if I also changed this other thing, then I could have life again. So what you really have to do is look at a very multidimensional parameter space and ask how many regions are there that can have life. And I think it's quite possible. In fact, that was in a subsequent paper. I've only written 2 papers on this out of the 150 something I've written. This is not my life, okay? This is just something I did on the side, where we considered that kind of thing. And many papers do talk about that. First of all, there are some things that if you change them, you just simply crush the possibility of life altogether. And I mean, there are some changes you can make to the laws of physics that are actually not very big changes, very small changes that would just completely, unambiguously rule out the possibility of life. But even considering those changes, which might be compensated by other changes, I think one can argue that you wouldn't expect that whole multidimensional space to be dense with such points where life is possible. They're probably still isolated islands in a sea of universes that are not viable. Okay?